it's my intention to one day return to society. And in preparation for that, I've decided to subscribe to societal norms, and I washed my hair today. I hope you enjoy it. You're more likely to enjoy the lecture than my hair, though. Well, maybe they'll be tied for last. But today's lecture is a handling of the conceptual view of a single sample experiment. And as I'll say when I talk about the slides, it's a little bit of a redux of that review chapter. That's not by accident. I did chapter 6 differently than your textbook author did last semester in preparation for this semester. I've now asked you to review that, and now I'm going to kind of hit it again so that you really understand how a single sample experiment works. We'll do half of the lecture this week and half next. The next half will be the calculation itself, and that calculation will involve something called a single sample t-test. We talked conceptually last semester about something called a single sample z. They're very similar. They both work in single sample experiments, but they differ in regards to the assumptions. And I remind you, the assumptions for a statistical test are the things that must be true of the population for that test to be appropriate. Tools for the job, right? All semester long last semester, and I'll do it again this semester, I'm sure. I talk about statistics and research methods as being tools for a particular job. The z-test and t-test work for the same method, but there are some specific assumptions that differ. I'll say more about that next time. These lectures, hopefully this semester, will be a little bit briefer, though this introduction isn't proving it so. And I'm going to try to slide in bits of video that aren't me, of other people, of other examples, that might help make some sense of this. All right, I'm going to stop talking. Let's talk a little bit about single sample experiments, building towards the very famous single sample t-test. So this will look familiar because we've just reviewed chapter 6, and chapter 6 is about the single sample experiment. We're talking about it again here because we want to learn a test that will allow us to analyze data that comes from a single sample experiment, but I hope you'll indulge me. I'm nothing if not repetitive, but I want to make sure you get this, because the logic of inferential statistics starts here, started with chapter 6, continues here. And once we get it, then it will continue. Nothing will change. The test will change, but the steps and the logic and the rationale and basically the process will be the same, whether it's a single sample experiment, a two sample experiment, a factorial experiment, a multivariate experiment. Should I keep going? I'm not going to. So I hope you'll indulge me as I potentially beat this dead horse a bit, but I promise you it's providing you with a foundation that will pay dividends by the time we're done. So a single sample experiment, again, we have a population that we know some things about. And from that population, we draw a sample. And of course, the idea here, which dates back to last semester, is the sample is meant to represent the population. And if the sample truly represents the population, then these two things should be equal. The population and the sample are the same, not just on one thing, but through random assignment, or rather random selection, to be more precise, it should be equal on all things. Ethnicity, age, height, weight, political party, favorite ice cream flavor, color of their car, how many cars they own. You get the idea. All of those variables should translate from the population to the sample. That's what random sampling is meant to do. That pause was because I couldn't remember where to pause the video so I could cough. So my apologies for that awkward moment. You get used to my awkward moments, yes? Lots of practice. So when we have a population, from it, we draw a sample. And we develop our statistical hypotheses. Again, you just saw this. I'm going to make you see it again. We have two basic types of hypotheses, and it will always be true. We have what's called the alternative hypothesis. The alternative hypothesis, abbreviated H sub A. And then we have the null hypothesis, abbreviated H sub 0, or sometimes O. What's the difference? Well, the alternative hypothesis describes what we would expect if our sample mean does not represent the population. What I mean by that is that we're going to expose that sample to some manipulation of a variable. And if we propose that that manipulation changes the sample so that it no longer represents the population, that's our alternative hypothesis. The null hypothesis suggests that there's not going to be a change. Null means no, right? The lack of. And this is what we describe if the sample and the sample and the population are not different, if they remain the same. So if the alternative hypothesis is true, then our population and our sample are no longer equal. And we say that that difference is due to the manipulation of the IV having changed the sample. They started out the same, now they're different. If the null hypothesis is true, we say that they're still the same. And they're still the same because our manipulation of the independent variable on the sample had no effect. We tried to change the sample so that it was different than the population through that variable's manipulation, but it didn't work. That presumes, however, in the alternative hypothesis, that they were equal to begin with, meaning they're not different simply because of sampling error. And so one of the things the statistic will allow us to do is to see if they're different, and then try to determine through probability how likely it is that that difference is due to the IV and not simply due to sampling error. The null hypothesis, again, states that they're not different. Or that if they are different, their difference is only due to sampling error, not due to the independent variable's manipulation. So to look at this another way, we have the alternative hypothesis. The sample no longer is equal to the population. We say the IV had an effect. Or it didn't. The IV had no effect, which leaves our sample and our population still the same. The rub, the trick still, however, is making sure that those differences or lack of differences are real and not simply due to sampling error or measurement error for that matter. So with this kind of conceptualization in mind, let's go through a potential single sample experiment. Hey, sorry to sully this lecture with my face, but I wanted to slide a video that's not mine in here before I go through my example. The thing is, the more examples you see to understand conceptually how this works, the better. And as I've said many times now in the course of this lecture, I'm beating this horse dead. So I thought it'd be good to slide somebody else's view or example in here, and then I'll go on to talk about my example as well. I'm going to do this a lot, just to try to give you a second way of thinking about this as we go forward. Okay, well, listen to this dude, and then listen to me. But here goes my face. Bye.
One day, you're hanging out with your buddy Kian, discussing politics and philosophy, and of course, your upcoming statistics exam. And in this conversation, he decides to tell you that his IQ is 130. And in case you weren't aware, 130 is indicative of extremely high intelligence. Based on some of Kian's political opinions, you're a bit skeptical of his claim. So you decide to put him to the test. You get your hands on 4 IQ tests, and you have him take all 4. Over the 4 tests, he scores an average of 128. Based on this, do you believe his claim? You probably would. If his IQ really is 130, scoring an average of 128 over 4 tests is quite reasonable. And the slight dip below 130 could be due to many things. We wouldn't really expect him to score an average of exactly 130 points, and this small deviation was likely due to chance. Now, let's consider a different scenario. Suppose instead that over the 4 tests, Kian averaged a score of 80 points. Would you believe his claim of having an IQ of 130 now? Probably not. And why is this? If his IQ really is 130, averaging a score of 80 is quite unlikely. You'd likely reject his statement that his IQ is 130. We understand that sample estimates vary around the true value, but are never really exactly equal to the true value. So the question that must be asked is, How far does the average need to drop below 130 before we think that Kian is a liar? Would we think that he's a liar if he averaged 117?
This slide, this ugly little slide right here, and it is ugly too. I'm a little out of practice on the design part of this from the summer, so my apologies. They'll get better as we go. But this ugly little slide right here, I've had to re-record now. I think this is the 5th time, so I'm trying to laugh to maintain my rage, but it's making me nuts. So ugliness aside, I wanted to walk you through a real experiment. And it is kind of a real experiment, actually. A former student of mine, Kelly Sheehan, Dr. Kelly Sheehan, has her PhD now at Northwestern, or from Northwestern, I should say. And she did an experiment as part of her job, and my daughters were participants. And so I've simplified it a little bit here for you, but it serves as a pretty good example of a single sample experiment. Because I'm pretty sure, they didn't tell me the exact design, but I'm pretty sure they did a single sample experiment. So in our study, we're studying children. So our population is kids. And from that population, we draw a sample of kids, right? That's how sampling works. And we're going to expose that sample to a variable to see if that sample differs from the population as a result. That variable is a free ABC Mouse account. My 2 daughters who took part got a free year subscription to ABC Mouse. And ABC Mouse is this kind of expensive, bougie online learning site and app. And, it's marketed to kids who are struggling, but it's really being sold to rich parents who feel guilty that their kids aren't going to be super geniuses or want to make sure that they're super geniuses. It's a little bit embarrassing. But it's a fun little game, and the girls do like it. But the idea is we, talking about our experiment, will give this sample free access to ABC Mouse. And then we're going to use a reading assessment to try to determine whether or not our sample differs from our population. And if it does, if that difference is a function of ABC Mouse or, as always, the potential sampling error. So in this example, our IV is access to ABC Mouse, and our DV is the score on the reading assessment. We manipulate our sample by giving it access to ABC Mouse that our population didn't have, and then we measure the effect that might have had on reading. So let me give you a couple of examples of our hypotheses, or at least our potential hypotheses. For my alternative, I'm going to propose that our sample shows improvement compared to the population. I'm presuming that the idea here is that having access to this reading program and writing and math program will improve the scores of the sample. The null hypothesis would be that those scores in the sample did not show improvement compared to the population. So our alternative hypothesis, ABC Mouse improves the scores on reading. Our null hypothesis, ABC Mouse does not improve the scores on reading. Now, the way we would write that would be something like this. The alternative hypothesis is that the sample mean, capital M, is greater than the population mean represented by the Greek letter mu, remembering back to last semester. Now, the null hypothesis is always the opposite of that there was no effect. But to best describe the sample will not show improvement compared to the population, we have to say this, that the sample mean is either equal to or less than the population. You can not show improvement by not changing at all, remaining the same. Or you can not show improvement by getting worse. So we have to write it this way. The mean is less than or equal to the population mean. Because we predicted a particular direction, we predicted improvement, I remind you that we call this a one-tail hypothesis. We're being very specific in predicting which direction this is going to go. So this was a real experiment, and this represents our kind of example experiment here. Now, it's a one-tail hypothesis because we predicted direction. We could do it the other way. Take a look at this. In this case, the alternative hypothesis is simpler. The sample will differ from the population. The mean is not equal to mu. Our null hypothesis is also simpler. The sample will be the same as the population. The mean is equal to mu. So 2 different ways to do this. One tail, two tail. I tend to do two-tail hypotheses. We will tend to do two-tail hypotheses in our class. But an experiment like this, the more realistic example is probably the one tail. They want to know if they're improving scores, not just changing scores. We might have something like this, where our population reading score was 13.5. I made these numbers up. Our population reading score was 13.5, and our sample reading score was 15.1. And look, it's obvious. First, takes you 10 seconds, not even 2 seconds to say, yes, 13.5 is not equal to 15.1. And if only that were the end, we could say, aha, I've got it. I have support of my alternative hypothesis. But the question again is, yes, these numbers are different. But are these numbers different because of our manipulation or simply because of the random fluctuation and error that we get when we sample a population? That's what we use inferential statistics to do. We try to make our best guess. Is this difference real and therefore a function of our independent variable? Or is this difference just sampling error? This is the 3rd time, I think, we've seen basically this same slide. We create what's called the distribution of the null. And we set a boundary to say that this is the probability that is too unlikely. That if our scores fall here, then I'm going to argue that our score does not belong on the null distribution, and therefore we can reject the null. We call that our region of rejection. And next week, we're going to work through these actual problems. We're still staying conceptual here. But we take, and again, you've seen this before, we take that score, we place it on the distribution. So if our sample mean falls here, then it probably belongs on the null. And we presume that our null hypothesis is true. If it falls here, we'll presume that it belongs on our null distribution and our null hypothesis is true. If it falls here, then the probability that it belongs is really low. So we will reject it and say that our alternative hypothesis is supported. Same here. This is super, super, super unlikely to belong here, so we reject the null and support our alternative hypothesis. If it falls in that region of rejection or not, we either accept or reject the null. Reject, accept, accept, reject. You've seen this again, right? We've seen this slide now thrice. So, this is all we need to worry about conceptually in this lecture this week. The slides will continue next week, and we're going to actually walk through the actual calculation here. I think, I warned you I was going to beat this dead horse, and I have. I hope you have some semblance of an understanding of this process, but it won't really make sense to you probably until we do some calculations and actually walk through the problem. So let's get to that. That'll be next week, and this will pick up then. I think I need to buy a hairdryer. I can't really get a haircut. My hair's going to get really long, and it's still wet. It just stays wet all day, I guess. This is not news to many of you, but this is something I'm just realizing. So I hope that made sense. It was review to a great extent, kind of applied to in a new direction. And proving that, I had some slides kind of repeat themselves. That's not going to change here as we go through part 2 next week. It's the calculation that's really going to make the difference here. I'm hoping though that by repeating this a bit, maybe even getting on your nerves with my repetition early here, that the logic of inferential statistics begins to sink in. Because the truth of the matter is, the z-test, the t-test, whether it's single sample, two sample, dependent sample, the f-test, which you might know as analysis of variance or ANOVA, even the MANOVA, the multivariate analysis of variance, they all work the same way. You determine a value, an obtained transformed value. You place that transformed value on the distribution of the null. Create a critical value which represents the probability that's too rare for you to believe that it belongs there. If your transformed obtained value falls beyond the region of rejection, or within the region of rejection beyond the critical value, you reject the null. If it doesn't, you fail to reject the null. Or if you want to say, you accept the null. So we're just going to do this over and over and over again with different tests all semester long. So if it didn't click right away, or if you're a little slow on the uptake on inferential statistics, that's okay, because you're going to get lots of practice. All right, see you Thursday.